technical glitch. I wasn't able to record. So today we're going to talk about motion, and under this we'll have three subtopics: kinematic quantities, displacement versus distance, and uniformly accelerated motion. So we're going to talk about acceleration also. So these three topics are very important, and now you can probably see the importance of having looked at vector operations such as multiplication, especially addition. So this is where we start to apply that knowledge. So it's good if you have done your due diligence, your homework. You might be very well prepared for this. You are better prepared to tackle this topic. It's very important because we live in a world where we are surrounded by moving parts, moving objects, machinery, nature, even looking outside into the outer space, the universe. Everything is governed by some sort of motion at any given moment. So it will be a very important topic to cover. It's a broader topic, so today we're going to cover these first three subtopics, and hopefully it will enable us by the end to be able to at least know and really grasp the kinematic quantities of velocity. Already we have some idea. Position is related to displacement. Actually tells us where an object is at a given moment, and also it will be very interesting to look at uniformly accelerated motion. Now, talking of kinematic qualities, we can see that in uniform movement we have speed, but in this case, since now we are talking more about displacement, displacement can be rendered in terms of position. As we can see here, we have a velocity being equal to the change in position over change in time. This is very important because the position is where the object that is moving is at a given time. So when we know where it was, we have a point of reference. We are able to know how fast it has changed its position. And it's a broader way to look at things because not everything will be moving in a straight line. Now, when we have the change in position, it's possible for us to express the change in position in terms of an arithmetic operation. So S sub I represented the initial position of the object. So S sub I means the position in relation to the reference. The initial usually 0, and down S means the current position. So that since V is equal to delta S over delta T, we can see this delta S actually is the change in position, and therefore we can derive a new equation from this. If we think that the initial position is 0, so we'll have the change in position over T. As we can see here, since the position is 0, we will have the change in position in terms of the change in time. So time will always begin at 0. Well, in this case we will consider the initial time as 0 for the sake of argument, for the sake of what we are trying to derive here. Now that means we can multiply by T both sides, so we can get this equation. So we can see that we just went too quickly there. How do we get to that equation? So we can see that we have T dividing there, the time is being divided by. So let's do this step by step. So we have V would be equal to the change in position, that is current position minus initial position over time. So we know that initial time was 0. So multiplied by T both on the right. What you do on the right, you do on the left. It's an equation. Therefore, VT will be equal to initial current position minus initial position. And what can that give us? What if we were looking for the current position? So it's a matter of sending this S initial, that is the current initial position. It's being subtracted, so we can add what we do on the left, we do on the right side. We add both sides, so we cancel that on that side, and we can finally express the current position of the moving body as the initial position plus the product of its velocity times time. So this brings us to this equation, the first equation of motion, a very important equation. As long as we have a constant velocity. The velocity doesn't change. We can always be able to tell where the object is at any given moment using this very important equation. So this is the first equation that will help us in kinematics, in motion, in movement. For example, we can solve the following question. Two cyclists start moving simultaneously towards one another from rest. The first cyclist moves at a speed of plus 6 meters per second. This is important, the plus, because this tells us that this is velocity. And the second cyclist moves at a velocity of minus, there is a minus missing there, minus 8 meters per second. Now calculate the time and position of their convergence. That means the time when they meet or they cross one another. So we are told that the initial position of the first cyclist is 0 meters, while the second cyclist is positioned at 112 meters. So we have data here. So we move on now to analyze how we can display our data. Before we solve, it's always good for us to see what we have on hand. What are the variables we have, and that will help us to see if we are in the first place able to solve. So we start with data, what we have on hand. So looking back at the enunciation, we go back to the problem, we see that the initial velocity, so we have two cyclists here. We have cyclist A and cyclist B. So we move back to check again, so we can just wrap around our heads. So we have cyclist A, but we realize what we need indeed is velocity of cyclist A, which is plus 6 meters per second. And in that way we also realize that we have cyclist B. What about cyclist B? What's the velocity of cyclist B? It's it's very difficult to write on this PP presentation, so this means that we have to try and insist or otherwise move on to a new form of explanation. Let's see if it works. Let's see. Yes, so cyclist B will have a we'll have a velocity of minus 8. So it's minus 8. Moving back, we have to check. So it's interesting, if he's moving at minus 8, it means he's moving in the opposite direction. So minus 8 meters. Okay, oops, so we have the issue again. We have the annotative issue. I'll have to figure this out. But for now, what I think we can do, forgive me, let me just move on from the PowerPoint. For us to solve this problem, I'll just have to move on and use another means. Let's just drop the presentation for now. Okay, we keep the changes for now. Okay, let's keep the changes, but we will not dwell on the changes that much. What can we do? We can find another means of sharing. So I'll share a different screen with you where we can be able to really solve this problem with success. So we'll move on from the PowerPoint for now so that we can share the working in a different environment, because as you can see, the slide presentation is presenting issues when it comes to writing down. So I'm just moving from that right now. Just a moment, sorry. Allow me to move. So now I'm sharing you this blue screen. So here we'll be able to annotate without any major issues. So going back to what we had, we had the data. We were doing the data. So as we were doing the data, we knew that the velocity of cyclist A was plus positive 6 meters per second. So let's write it also nicely, meters per second. And the velocity of cyclist B was minus 8 meters per second. So this is a scientific way, more scientific way to write meters per second, considering exponential form. And what else do we have as data? So I'll go back to the exercise. You know that cyclist, the position, initial position, which we'll call S sub IA, initial position of cyclist A was 0 meters. So he starts from the origin. Now cyclist B which is S sub IB. We are told it starts from 100 to 112 meters. So he's 112 meters from the origin, from cyclist B. Interesting. So we want to know where they meet, at which position, and the time at which that takes place. So how do we do that? What do you think? How do we go about solving that part of the problem? Well, we have to reason. We can reason that for that to take place, their displacement, their positions, should be the same. So S sub A should be equal to S sub B. The position of cyclist A should be equal to the position of cyclist B, of course, when they are meeting, when they cross. So now, what is the position of A by itself? Well, cyclist A's position will be given by the equation we just learned about, which is based on the initial position of A plus the product of the velocity of A times the time. And interestingly, at this moment, time is the unknown. So we are looking for time. But now let's move on to create a system of equations. What about cyclist B? What's his position given by? In the same manner, cyclist B is given by the same equation that we just learned. So it will be cyclist B position, S sub B, will be equal to cyclist B initial position, S sub I B. So that's cyclist B initial position, plus the product of cyclist B's velocity times time. Notice that time is the same variable there, so we have something in common. Normally we say that we have two equations, and how many variables? We have time, which is an unknown, and we have the positions, which are an unknown. But when we have two equations and two variables, we are able to solve. So what do? We will, since we said the position of A is equal to the position of B, it means that these two circled parts of the equations are the same. They can be equated. So let's do that. But before we do that, we remember that of course the initial position of cyclist A is equal to 0, right? So we don't actually need to add it, right? It cancels out. So initial position of A is 0. So we leave that out in order to avoid confusion. Let's just start with the velocity of A multiplied by time should all be equal to the initial position of cyclist B, which is S sub IB, plus the velocity of cyclist B times time. So looking at this, we can continue to rearrange it. We can perhaps send the product of velocity by time. We can put it on the same side. So here it's adding, so we send it there by subtracting it. Let's subtract both sides of the equation. What do? We subtract both sides of the equation we subtract VB times T. So we could choose to do that. So we have VA times T minus, so we have done the subtraction here, minus VB times T will all be equal to the position, the initial position of B. But we could be fancy and really do a little bit of remove a common factor there, that variable T. We can put it out, really. We can leave it out, and then when we leave T outside, we will have the velocity of A minus the velocity of B, all equal to the initial position of cyclist B. So what does that leave us with? We can divide both sides by the variable initial velocity, by the arithmetic operation there. We can divide by velocity of cyclist A minus velocity of cyclist B. What we do on the left, we do on the right, of course. That's the principle of equations, so that we can cancel out. That divided by that gives us 1. So in the end, what do we have? We have that the time when it occurs is given by the initial position of cyclist B, all divided by the difference between the velocity of cyclist A from the velocity of cyclist B. So what does that give us? We plug in the data now. We plug in the values. So what is the initial position of cyclist B? So we know that's 120 meters. We specify units. We'll see how it helps to always include our units. It helps us to see exactly whether we're on the right path or not. So 6 meters per second minus, what is the initial velocity of cycles B? Minus my, so we have to be careful. We open brackets because velocity of cycles B is already negative. So we open brackets, minus 8 meters per second. Well, I left the meters per second outside the brackets. Now, minus, that is the same as just crossing those two minuses. And then we'll see what we get. So 112 meters divided by minus 8. So basically that's equate to 6 plus 8, which is 14 meters per second. Meters per second. So what is 112 meters divided by 14? So you see that what happens to the units. The units cancel out. M divided by M is 1, so it cancels. Now we have only seconds. So our time will be given by 112 divided by 14, which will give us the time of how much? Check your calculator. That gives us 8 seconds. So basically these two cyclists will cross one another. They will meet at the 8-second mark. That's where they will cross or even collide. So let's see. But the question requests us to also to show at which location will they be. We know that cyclist A started from 0. So where will it be? How far will it be from the origin? And the same applies to cyclist B. But they will be at the same position. So if you calculate for one, we're as good as calculating for the other one. But let's start with cyclist A. Where will it be? So we can now apply the same equation, only that now we have an additional amount of data. So the equation tells us that the position of cyclist A will be given by the initial position, which is 0. So we just write it here just for the sake of correctness. So times plus velocity of A times time, but we know that that is 0 since cyclist A begins from the origin, from the initial position 0. So basically cyclist A's position will be given by the product of cyclist A's velocity multiplied by t, the time. And since now we have the time, it's a matter of multiplying the velocity, which is plus 6 meters. So the units here, meters per second, multiplied by 8 seconds. So notice that the seconds on one side are being divided, so meters per second. So these seconds will cancel these seconds that are multiplying. So what you have will give you in meters. So it's a matter of saying 6 times 8 m will give us 48 meters. So we understand that these cyclists will meet or collide or cross at the 48 meter mark. After 48 meters of traveling, cyclist A after 8 seconds will meet with cyclist B. We can confirm that. Will it be in the same position? Remember, this is position. So let's check using the same equation now for cyclist B. Cyclist B's position will be given by the initial position S sub IB plus the velocity of cyclist B multiplied by the time. So time is the data. We have that initial position of cyclist B is 112 meters. We have that from the word gone. So 112 meters plus the velocity of cyclist B. We remember to open brackets, since this velocity from the beginning we know it's negative, which means it's just going the opposite of cycles A. So it's 8 meters per second. Interesting. Now the time has been calculated. It's the 8-second mark. So we plug that in there, and again we remember to cancel out, check out the units. We are adding 112 meters. So 112 meters, how can it add with meters per second? Something has to happen there for this to be coherent. So we remember there's a minus sign also, so cancels this. So we cancel the seconds because one is multiplying, the other is dividing. So we have 8 times 8, and it's a negative, so 8 times 8 is 64. So what is the difference? What is the difference between 112 minus 64? That will give us 48. You can check if you check, you will find that it's 48. So this is coherent. It makes perfect sense. These two cyclists will meet at the 48 meter mark from the origin. So the only difference is that one starts from the origin at 0 at the reference, and the other is coming to meet the first one from the 112 meter. We can depict this. Perhaps it can help us to grasp it even better. So we can say cyclist A. There we have cyclist A going towards cyclist B. In this case, we'll choose him moving to the right. So that's the 48 meter mark where they will meet. Now, cyclist B, okay, that's the direction. Cyclist B moving in the opposite direction, which explains the -8. Will be moving, you see, cyclist B moving in the opposite direction. So we show here so let's stretch and see where cyclist B starts at 112. Oh, sorry, let me rewrite that. So it's at the 112 meter marker. He moves towards cyclist B. So they meet at the 48 meter marker, 48 into the initial position, which is 0. So we can see that the first equation of motion is very useful. It can help us to find the position of objects as they move in a straight line. That's very important also to take in mind, to consider moving in a straight line. So now let's move on. After having seen this, we have to see how this can be displayed we move on to to talk about displacement. So we go back to our presentation after we have calculated. Let's check out the answer that we were looking for. Indeed, if we move on, indeed 8 seconds, 48. Of course, I missed the units. 48, those are meters. So that was that. So we move on to another concept, the concept of displacement versus distance. So remember that we spoke about vectors and the importance of vector quantities and scalar quantities. So simply put, distance is a scalar, displacement is a vector. So how can we graphically display that so that we can get a full understanding? Well, suppose you were moving from point A. Let's assume you are moving towards the north, starting from point A, and you move 3 units. Let's not say whether it's centimeters or meters or kilometers. Let's just say 3 units of distance. You move to the north 3 units, 1, 2, 3. So you have moved the distance of 3 units right there, and let's call that point O. You move to point O, from point A to point O, and you've moved 3 units. That's the distance that you've covered. But suppose you have a necessity to turn left or to turn eastward and move 4 units. You see? So now you turn, as you reach point O, you move on to point B. You move 4 units of distance. So basically, you have moved a total distance of 7 units. I'm used to using meters, so that just flows out naturally. So you have moved some 7 units. And that can happen really in real life. Maybe there's an obstacle. I think of a mountain, but really, right now, let's just think of a block of buildings, or even a single building. It's 3 meters. So 3 meters might be just a house, you see. So you go around the house because you can't really go through the house. So you've moved 7 meters in this case. If it's a room, a 3 by 4, I believe that this is what we call a quarter. So a 3/4. So you have moved. But now suppose you have the same situation where you are going to move to the north, towards the north maybe 3, and then turn to the left, to the east, turn 4 units. But in this case, instead of following that trajectory, instead of following that path, you had a possibility. Maybe the ground is flat, the landscape doesn't have any obstacles, and then you have the possibility to just go straight to point. By the way, this is point B. I should have mentioned that that's point B. You could have moved straight without going to point O. You could have moved straight to point B from point A. What is that? So this is where Now we recall that we learned vector addition, because simply saying the distance from A to B is 3 plus 4 would be wrong. Wrong. So this is where we have to apply what we discussed in the last lesson on vector addition. And this is where I'm sorry if you thought you had gotten rid of some aspects of mathematics, trigonometry, you'll be disappointed, because trigonometry is still with you. So this distance, let's call it the shortcut distance, we'll call it R. I like R because it rhymes with resultant, what we're going to find, especially in other books, a resultant. Now let's redraw this triangle that is originated. We can see just by moving to the north 3 points and then 4 points to the east, that describes 90-degree change of direction. So this helps us to see that, okay, here we have a right angle triangle. And some of you who like trigonometry know that if you have a 3 and a 4 in a right angle triangle, you get a 5, in the hypotenuse. But okay, let's do it step by step so we can see how we get to that number, to that 5. Let's redraw our triangle facing this side, which is the most common way to visualize it. So 3, and then here you have 4 at the bottom at the adjacent, and then you have the angle of 90 degrees, the right angle, and you have R that you want to calculate. So 90 degrees here, you have R. So can we use sine theory? Maybe not, because we don't have the value of the opposite angle, but we can use another Pythagorean, the Pythagorean theorem basically, which tells us that we can use the square of the hypotenuse R, in this case, will be equal to the square of 3 plus the square of 4. Really, that's how we can find the value of R. And now we just have R squared with square R squared to cancel out. And of course, what we do on the left, we have to do it on the right. So we also square everything that is on the right. In this case, 3 squared plus 4 squared. And if your mathematics, your calculation brain is fresh, you obviously see that, okay, 3 squared is 9 and 4 squared is 16, and that 9 plus 16 is 25. So you're looking for the square root of 25. Now the square root of 25 is 5, and do we have to write that? No. So the square root of 25 is 5 units. So that explains what we got there. 5. We were correct. That's the correct way. If you said 5 in the beginning, congratulations, you got it. So in this way, we can see the 5 units or 5 meters, that is the displacement in comparison to the 7, which is the distance covered. So definition tells us that displacement is change in position. It doesn't matter whether you went to the north, to the south, you went around and you went down. The displacement just represents what you moved from point A and your last point, which is point B. That's your displacement, that's very important. You see, it doesn't matter whether you had to go up, go down, and sometimes displacement can be 0. If you go around and you stay back, you stay where you started, that's displacement is 0. So what about distance? Distance now considers something different. The length of the path followed, which means now you care about the energy you used. You really considered, no man, I had to go to the left, to the right. So that's distance. That's distance. So it's not a straight path only. It's actually what you covered, you physically, where you've been. That's the distance until you go to the point. So really, that's the difference. While displacement is a straight line, distance may not follow a straight line. So that takes us to the next point, velocity time graph. Since we have to express this in the VT graph, in the velocity time graph, when we are talking about constant velocity, because the previous equation works for constant velocity when velocity is not changing. So when velocity is constant, how do we visualize it? Well, we have a graph just like this one, where in the y-axis we have the velocity and the x-axis is representing time. The constant velocity is simply since it's a constant. If you remember in mathematics, most of the times constants are a horizontal line. So it will simply be a straight horizontal line. That will be how we will display the velocity in a constant velocity VT graph. Now, something interesting about this, let's move on. Okay, shall we? Something interesting about a VT times graph is that, as you can see, you can apply, if the velocity is constant, you can apply the first equation as we said. Now, the velocity must be constant for this equation to work. If the velocity is not constant, please do not apply this equation. Now, something that might come to mind, when we have a graph like this, we can notice that we have something else. We have the area that is formed by this graph. In other words, the area below the graph. So we have V. It's a VT graph. So it's not V minus T, it's a VT graph. That's another way of calling the velocity time graph. So it's a VT graph, but we notice that, okay, we can talk about the area that I'm shading right now. So what is represented by this area? Well, we don't have to be rocket scientists. We can come and see VT graph. The area under the graph, if we even consider our equation, our formula, it represents position or displacement. In fact, it represents distance. We have to be accurate about that. It represents the distance traveled, regardless of the displacement. So in the VT, the area below the VT graph represents the displacement, as we will show right now. So constant velocity, straight line. So constant velocity, straight line. So let's pull our equation. We know that it will depend on the initial velocity, which for the sake of our reasoning right now, we will equate to 0, assuming that it starts from 0, so we can get a generic equation for the area below the graph. So initial velocity cancels out because it's 0. So in the end, the distance will be velocity times time. Of course, here we are showing displacement because it coincides. The distance will coincide with the displacement in this case. So you can see that you multiply the vertical by the horizontal VT, you get the area below the graph representing the distance covered, and in this case also coinciding, representing the displacement. So the area of a VT under a VT graph represent the distance covered. For instance, if you had an object moving at a velocity of 4 meters per second, and maybe after 16, why not use a better number so that we can get a fancier number? Let's use 24. So after 24 seconds, you will want to know, okay, moving at 4 meters per second, where will it be after 24 seconds? Well, happily we can apply our recently learned position equation. So we enunciate it, and this time we know that the initial velocity is 4 times the time, which is 24 seconds. Now you see what happens to the units: 4 meters per second and then 24. The seconds cancel out, they divide, and we will have our answer in meters. So 4 times 24. So that means 24 times 2 will be 48. 48 times 2 is 96 meters. So it means that in this example, our object has moved 96 meters all the way. So it shows us that the area under a VT graph represents the distance covered. Now, what else can we say about a VT graph? Well, this will help us to transition to the uniformly accelerated motion. Now, we are bringing in a new word: uniformly accelerated motion. You can see that uniformly continues to mean a straight line. But now there is something strange: accelerated motion. What is this accelerated motion? Well, we can explain it by considering the graph, a VT graph. Now, the only difference in this VT graph from the previous VT graph is the nature of the line representing velocity. What's the difference? What do you see here? Of course, if you say it's inclined, it's tilted, it's sloped, you are correct. This line is sloped. It has a slope. It has a gradient. So, and it's got an inclination. It's inclined. What does this mean? What does this tell us? Well, the inclination tells us, for one, that the velocity is not the same at all times. As the time passes, the velocity changes. That is what we call acceleration. Of course, acceleration can be negative. So this graph could be facing downwards, which means that we will be looking at it as deceleration. But now we're looking at an acceleration. And what else can we say about uniformly accelerated motion? We can consider how we can derive a new equation for accelerated motion, because this equation, this motion is different from constant velocity motion. Remember, in mathematics, we used to say we could calculate the gradient of a line by considering the change in y and then considering the change in x. So gradient was m, which was equal to change in y over change in x. So the amount of going up, considering compared to the amount of going left or right. So that was what we call the gradient. Similarly, since velocity is on the y-axis and time on the x-axis, if we could consider the change in v over the change in t, we will be calculating a gradient of a vt graph. And we know that the gradient of a vt graph now will give us acceleration. So acceleration is by definition the change in velocity over change in time. But it doesn't stop there. Acceleration being change in velocity over change in time. We have a definition. The slope of the vt graph represents acceleration. It's true graphically, but the definition, acceleration, is the rate of change of velocity. The rate of change of velocity. So it means how much you change your velocity. For example, if I was moving at 3 meters per second and then 3 minutes later I was moving at 4 meters per second, and then 6 minutes later I was moving at 5 meters per second, 9 minutes later I was moving at 6 meters per second. So you can see there's a relation. Every 3 minutes I up my velocity a notch, I increase my velocity by 1. So that is what acceleration is. Of course, the same can be applied if I'm decelerating, I'm reducing my velocity. So the rate of change, how fast do you change your velocity? And for that, we have a small video here. We can see acceleration of a Ferrari. So we speak about powerful cars that can accelerate very fast, very speedily. You can see that it went from around 0 kilometers per hour to 100 kilometers per hour before it disappeared from the image. Before it went out of our view there, it was already above 100 kilometers per hour. So we say that such a car is very powerful, because also as you will learn, power is the rate of change of energy. So in this case, acceleration is the rate of change of velocity. It was slow and then became super fast in a very short period of time. So that is what acceleration. The change in y over change in of x happened in a very steep slope in this case for the Ferrari. So it's a very fast car. And cheetahs amongst the animal kingdom are considered to be very, very good accelerators. Actually, a cheetah may accelerate quicker than a Ferrari. The only thing is that it doesn't reach the speeds or the velocity reached by a Ferrari. But when it comes to moving from standing position or rest to high speed, cheetah is very fast. So it accelerates very fast. Now, let's talk about uniformly accelerated motion. Here, we are talking about a motion where the increase of the velocity will be done in equal intervals of time, as I was describing, moving from 3 meters per second and then moving to 4 meters per second in the equal intervals of time. That's what we call uniformly accelerated motion. That is why our graph that we drew earlier was a straight line. So remember, we can always mention uniformly as related to a straight line in these graphs. So now, because we know that acceleration is delta v over delta t, what is delta v exactly? Well, delta v is v, the final velocity, which we'll leave it as v. Some books will put a v sub f to show that, okay, it's final velocity, especially Latin and Portuguese books, Spanish, vf. But now we will consider initial velocity as u. This is universal, friends. If you consider the initial velocity as u, you will have less confusion in many books, many physics books that you read. So now we have v, which is final velocity, and it becomes, so let's write it down. V represents final velocity, while u, which in some books actually is v sub 0 or v sub I, so it's initial velocity. But here we'll use u, and I assure you, u is more universal. You will find u in many of your literature, of your books. So delta v actually is v minus u, final velocity minus initial velocity. So acceleration, by that definition, will be final velocity minus initial velocity. But okay, we have delta t. We mentioned earlier that delta t also simply means the t currently, the time that we're looking at, minus the initial time, which usually is 0 when we consider our reference as a starting point at 0. So in the end, we just have t. Delta t is will be summed up as being t. For example, in this case where we're trying to define and derive a very important equation, let's consider delta t to be t. You know, the initial time was, it started at 0. So our initial time is 0 in this case. So therefore, acceleration then becomes the change in v over time. So that is final velocity minus initial velocity divided by time. But this doesn't look that beautiful. Let's make it look a little bit more fancier by multiplying by t both sides. What happens? We multiply by t. Let's write that the equation again so we can see what we're doing. We multiply by t both sides. What we do on the left, we do on the right, because it's an equation, and therefore t divided by t cancels, becomes 1, and we move on to acceleration being, so we put a before. That's aesthetically pleasing to say a times t will be equal to final velocity, which is a v, a very well defined v, minus a very well defined u with a small tail, so that u is the initial velocity. Well, we want things to be positive, right? So let's get rid of that minus u. So we have to add it because it's being subtracted. So we add both sides, we add a u both sides. In the end, we have the final velocity. What we're trying to calculate is given by the initial velocity, be whatever it is, maybe 0, but any initial velocity of the object plus its acceleration times time. So that is the second equation of motion, and it's very important. In this case, applicable when the acceleration is uniform. When acceleration is happening in a straight line, we can use that important equation. And therefore, it brings us back to acceleration being delta v over delta t. You could see how we were able to derive that equation down left or right at the bottom right. That's how we derive it. And if we look at the graph of v, we can make a quick example of this. For example, assuming uniform acceleration, assume this is a straight line. Well, let's say we start with a velocity of 2 meters per second. Can we calculate acceleration or any other variable? Well, assuming we know that the initial velocity is 2 meters per second, and we know that this takes place during a time period of let's say we are considering a time period, okay, starting from 0 seconds and moving to a time period of what number can we use? Okay, so we want v at the end. In this case, let's say v is unknown, and this takes place during a time span of 18 seconds. Yes, let's say in 18 seconds, this object that started with a speed of 2 meters per second, how fast was it? What is the v? What is the final velocity of this object? But we need another data here. We need another data to make this make sense mathematically. So let's say we know the acceleration, 1.5 meters per second squared, and there indeed we should have mentioned this is the unit of acceleration, meters per second squared, which you probably know, but it's always good to remember. So 1.5 meters per second squared is acceleration. So what data do we have? First, we lay out our data. We define what data we have on hand, and we define what we want to calculate. So first we have initial velocity. In this case is 2 meters per second. Now it's not 0 anymore. You see, we're getting a little bit interesting. And next we have the time, 18 seconds. So all of this takes place within 18 seconds. And we also have acceleration given to us as 1.5 meters per second squared. And what we want here, we want final velocity. So that's the unknown. And you know, when we write meters per second squared, it's always good to know that you could write it like this also. That's another way of writing meters per second squared. So it's meters divided by second squared. Now our unknown is v, final velocity. What is it? So can we use our recently learned equation? You will be happy because the answer is of course. So final velocity will be given by initial velocity plus the product of, so final velocity, also we are substituting directly, we can say the initial velocity is of course 2 meters. Now the product of acceleration by time. It's good to write the units because they will help you see what's taking place here. Otherwise you wouldn't be able to add 2 meters per second to 2 meters per second squared. So you have to look at the units and see what's happening between 1.5 times 18. Okay, 18 is seconds, so there's a second there that is multiplying 18, but then you have a second squared that is being divided. If you considered minus 2, it's being divided second squared. So you cancel 1 second from 18, and only 1 from the second squared becomes 1.5 meters per second times 18. What does that give us? I will guess it may give us, because 2 times 18 is 36, and then 1 times 18 is 18. How about 27? No, let's see, does it give us 27 or 20 what? Let's check. Well, let's check our calculator. It gives us 27 indeed. So it's 27 meters per second, and you add that to 2 meters per second. Of course, that will give us a velocity of 29 meters per second, close to 30 meters per second. This is not a human being that is moving. This is probably a fast car. This is a car. Well, it moves from 2 meters per second all the way to close to 30 meters per second in 18 seconds. This has got to be a fast car. Has got to be a fast car that we're talking about right here. So there you have acceleration taking place in 18 seconds, a change in v of 2 meters all the way to 29 meters per second. That is acceleration for you. And then you have just applied the second equation of motion, uniformly accelerated motion. Let's do an example, a formal example. So a car is initially at rest, which means u is equal to 0. After accelerating at a constant rate, it reaches a velocity of 9 kilometers per hour after a time of 6 seconds. Determine its acceleration. So 9 kilometers per hour. Here, this is more a problem of conversion of units. Remember, we spoke about SI units, and we spoke about how some countries, use different types of units, miles per hour. So here we have a dilemma where we have 9 kilometers per hour after a time of 6 seconds. Something doesn't really coalesce there. So if you want it to work out, we have to do a conversion of our data. So we start by what we have. We have the data, for example, we say that the initial velocity was 0, so u is 0 here. So u is 0 meters per second, or in fact 0 kilometers per hour. But okay, we want to use SI units, so 0 meters per second. And what about the velocity it reaches? So that's its final velocity. That's v. V is 90 kilometers per hour. So that brings in, that spices up this problem. So we just have to convert. I'll give you a tip. If you come before a situation like this, you just divide by 3.6. You will learn this, you will use this a lot. If you divide 90 kilometers per hour by 3.6, it will give you 25 meters per second. That's a conversion. How do we get here, you might ask? Well, it doesn't hurt. Let's just do it step by step. How do you get to 25 meters per second? Well, you could say 90 kilometers is 90 times 1,000 meters. So that becomes 90 meters. 90,000 meters, sorry. 90,000 meters. 90,000 meters. But then you divide the 90,000 meters by an hour, which is 60 seconds times 60 minutes. What does that give you? It gives you 3,600. So 90,000 meters divided by 3,600. Forgive me, I'm doing this in the calculator. So 90,000 meters divided by 3,000, 60 times 60, which is 3,000. So this is a conversion, fast conversion. 3,600. So you, oops, it's 90,000 meters divided by 3,600 seconds. So what you get there, you cancel the two zeros both sides. You have 900 divided by 36, which will give you 25 meters per second. And there you have it, folks. The velocity we have, the final velocity, is 25 meters per second. What about the time? We are told that the time that elapses is 6 seconds. So elapsed time 6 seconds. Elapsed time is 6 seconds. And therefore, using our equation, so v will be u plus acceleration times time. We know that u is 0 since the car started at rest, but it's good for us to write it to see how it works out. So u equates to 0. So u is equal to 0. Let's plug in the values. So v will be equal to v minus u. So we are calculating acceleration here. Acceleration be v, because that's what we want, that's the unknown, it's acceleration. So we have to substitute for acceleration. Now we have substituted, we plug in the value, so it will be 25 meters minus initial velocity, which was 0 in a way, so what we have, 25 divided by 6, we see what happens to the units. 25 meters per second divided by 6. This second here is being divided by, and is being divided by a divided second. So what will happen is you'll have meter per second, which multiplies a neighboring second. So it's meters per second squared, which makes sense because really acceleration is meters per second squared. So what is the value? 25 divided by 6 will give us 4.17 meters per second squared. Of course, been rounded off, something like 4.16666. So that is the answer, folks. So you can see how we can apply the second equation of motion to solve the problems of accelerated motion whenever the acceleration is uniform. So this is what we have here. Because of time, we probably do not have enough time for you guys to carry on and do an exercise, by the way. So what are we going to do? A particle has an initial velocity of 12 meters per second, moves with a constant acceleration of 3 meters per second. Determine the time at which the particle stops instantaneously. So this, I'm not sure we will solve. We have time to solve. Let's check how much time has elapsed. So this is an exercise that it can be done. We can use the same equation. So the answer will be 4. You can do it and check. Now let's summarize what we just learned. The summary, so for uniform motion, the position equation is as follows. S will be equal to initial position plus the product of its velocity times time. In this case, we assume that the velocity is constant. So in a velocity time graph, it will be flat if the velocity is constant. We saw that. And we know that acceleration is delta v over delta t, change of velocity over time. So that is what acceleration, the gradient, the slope of a vt time graph, that will give us acceleration or deceleration. Now the velocity time graph has to be sloped but straight if we're talking about uniform acceleration. So that gives us an equation we can apply in those cases, which is v is equal to u plus at. View at, that's what I used to call it. That's what I like to teach my students. View at. So that is when acceleration is constant. So velocity is changing but gradually. So we can use that equation. And with that, dear friends, we've come to the end of our lesson. Feel free to ask questions. We have a platform for that. You can always present your doubts, any questions that you want to clarify. And I look forward to the next class. And okay, please make sure you do your homework. It will be posted on Classroom, on Google Classroom. So make sure you check that out and hand it in before the next lesson. That will be much appreciated, dear students. So that was it, dear folks. Thank you for your attention, for being part of the lesson, and looking forward to the next lesson. So this was another lesson of physics lessons on motion. So we're looking forward to doing this with you, courtesy of El Linguistica. So see you next lesson.